All right, in this example, we have a tank that's an inverted cone with a height of 10 meters and a base, which is at the top, right, because it's inverted, of 4 meters. So the base is 4 meters. I think it means in diameter. Should be diameter. It's filled with water to a height of 8 meters, and we're asked to find the work required to empty the tank by pumping all of the water to the top of the tank. All right, well, all right, so let's draw a picture. So we've got this conical tank, right? It's an inverted cone, so I'm going to draw the circular base at the top, and then let's see, let's put the center here. I'm actually going to put a y-axis down the middle of it. All right, and then let's put an x-axis this way. All right, just so I can get it all centered so it looks nice. And then the sides of the cone come down to 0. All right. Now it says the base is 4 meters wide, so that means the radius is 2 meters. And let's see, this is the y-axis, this is the x-axis. Let's see, what else do we know? We know that the height is 10 meters. So this is, I'll just put 10 meters here. Draw that in. And then that's filled with water to the height of 8 meters. So let me kind of draw a sketch in where that water level is. So let's put a little bit of an oval in here to indicate the water level. So the water level is at 8 meters. All right. And okay, so we want to find how much work it takes to pump the water out over the top of the tank. Okay, so we got to pump it to a height of 10 meters, right? All right, well, this one I think we're just going to have to break it down into slices. So I'm just going to take a look at one slice of water. Okay, so it's supposed to be an oval. So it has some thickness here. All right, the distance here is x, and its thickness is delta y. Okay, so we're going to look at one slice of the water. And if we can find the weight of the water, then we can multiply it times its distance, right? And then add up all of those. The weight multiplied by the distance gives us the work done. And then we can add up all of the work it takes to lift each one of these slices of water. Okay, so that's kind of the approach I want to take. So let's take a look at this. The volume, we're going to take a look at one slice. So the volume of one slice is just going to be the cross-sectional area, which is pi x squared delta y. All right. Now we're going to integrate it in the y direction. So we really don't want to have x. We would rather have an expression in terms of y. So let's take a look at the boundary of this this line that defines the boundary of the cone is essentially, okay, so rise over run, so 10 over 2. So this has a slope of 5, and then the y-intercept obviously is 0 down here. So this is the line y equals 5x. Okay. So if I want to rewrite that, I can write x equals 1/5 y. So now I have, oops, not y in the denominator though. That kind of looks like y in the denominator. Okay, 1/5 y. Okay, so I'm going to replace x with 1/5 y. So what I have is pi times the whole thing, 1/5 y, oops, y, that whole quantity squared, delta y. Okay, so that's the volume of one slice. And then if I want the mass of one slice, let me write that up here, I guess. So the mass of one slice is just going to be, yeah, it says here that the density of water is 1,000 kilograms per cubic meter. So we can take that times the volume in order to get the mass of one slice. So that's just going to be 1,000 pi times this 1/5 y quantity squared delta y. Okay, but what we really want is the weight of one slice. So we can write that. If we just take the mass times the acceleration of gravity, we'll get the weight of one slice. So the weight of one slice is equal to 9.8 times this whole thing, times 1000 pi times 1/5 1/5 y quantity squared delta y. Okay, so that's the weight of a slice. Now, how far do I have to lift any given slice? So all of these slices are different heights, right? And we have to lift it. The whole cone is 10 meters. So each slice must rise a distance of 10 minus y meters, right? So at the bottom, you know, this little, it has to rise the whole 10 meters, whereas at the top here, it looks like the top of the water is at 8 meters, so it only has to rise 2 meters, okay? So now that we have all of that, we're going to then just add up all of the work done to lift each slice of water. Okay, so the work is going to be the integral. We're integrating in the y direction, and we only have to lift the water, right? So we're just gonna, the water is goes from 0 to 8 meters. So we're going to integrate from 0 to 8, right? And so if I rewrite that, I'm going to take the weight of one slice. All right, I'm going to actually rewrite this whole as 9.8 times 1000 times pi times 1/5 y quantity squared. All right, I'm going to rewrite that. If I simplify that, I'm going to get 392 pi y squared delta y, but then I also have to take it times the distance, right, which is 10 minus y. So that's the distance we have to lift any given slice at is at a given level of y. Okay, and then dy, right? So I'm just basically taking the weight, right, which is the force it takes to lift a slice, right, times the distance we have to lift it. And if we do that, we'll get the work. So let's do that. So I'm going to pull this 392 pi out front. And then we just have to integrate. This becomes 10y squared minus y cubed. Okay, so I'm going to get 10 thirds y cubed minus 1/4 y to the 4th. Right, and then I want to evaluate that from 0 to 8. All right, so when evaluated 0, it's just 0. So I just need to evaluate it at 8. And so if I put this all into my calculator, what I get is 840,706.95 joules. Now that's probably way more significant figures than I need, but I'm just going to write it all out there. And that's my answer. That's how many joules it takes to lift all of that water from the tank out over the edge to 10 meters, essentially lifting it to 10 meters. Now it's kind of interesting. Essentially, you have to lift it from the top. So you have to have some sort of a hose or something that's sucking water off the top here in order to do that. If you put a hose all the way down to the bottom, then, you know, and you're sucking water off the bottom, then you have to lift it the whole 10 meters, right? All that water. And then so essentially gravity is going to do work pulling all the top water down. And then you have to undo the work that gravity did by sucking it off the bottom. So it's kind of, I'm not sure how this works. You have to suck the water off the top in order for this to be true. But anyway, it's just a problem to give you an example of how we can use integration to determine the amount of work done. All right, so that's pretty much all of the work problems. We have one more little topic, little subtopic to cover, and then so I have one more example on a different topic. So we're going to talk about hydrostatic pressure and force next.